Look up at the night sky. What do you see? A scattering of stars, perhaps the glow of a distant planet, or the faint band of the Milky Way stretching overhead. But what if I told you that beyond those familiar points of light lies a universe so bizarre, so utterly unpredictable, that even the most brilliant scientists are left speechless? Space isn't just empty darkness, it's a cosmic carnival of wonders, where the laws of physics twist into knots and reality itself seems to bend. And here's the wildest part, we're only just beginning to uncover its secrets. Picture this, a star that shouldn't exist vanishing into thin air, a galaxy shaped like a cosmic question mark, as if the universe itself is teasing us. Black holes spinning so fast they rip holes in the fabric of space-time. These aren't scenes from a sci-fi movie, they're real, documented phenomena discovered in just the last few years. Every time we think we've got space figured out, it throws another curveball our way, leaving us equal parts baffled and exhilarated. That's the thrill of exploration, the moment you realize the universe is far stranger, far more vibrant than anyone ever imagined. That's exactly what we're diving into today. 30 of the most mind-bending space oddities recently uncovered by astronomers. From rogue planets hurtling through the void to mysterious radio signals repeating like clockwork, these discoveries aren't just curiosities, they're rewriting the textbooks. Some defy explanation, others hint at forces we've yet to understand, and a few might just hold the key to answering humanity's biggest questions, so buckle up. This isn't just a tour of the cosmos, it's a front-row seat to the greatest show in the universe, where every discovery pulls back the curtain on something even more extraordinary. Ready to have your mind blown? Let's begin. The first oddity on our list sounds like something straight out of a cosmic thriller, a hurricane of dark matter barreling through our galaxy at speeds that defy logic. Astronomers call it the S1 stream, a colossal river of invisible particles racing through space at nearly 500 kilometers per second. Unlike the swirling storms we see on planets, this isn't made of wind or water. It's a torrent of the universe's most elusive substance, a ghostly force that neither reflects light nor interacts with ordinary matter. Yet here it is, slicing through the Milky Way like a silent, unstoppable tempest. What makes this discovery so groundbreaking? For decades, scientists have treated dark matter as a static, almost placid presence, an unseen scaffold holding galaxies together. But this hurricane shatters that assumption. It's dynamic, violent, and alarmingly fast, suggesting dark matter might be far more chaotic than we ever imagined. Even stranger, Earth might be right in its path. Calculations suggest our solar system could be passing through this invisible maelstrom, with trillions of dark matter particles flooding through us every second, utterly unnoticed, yet potentially leaving traces in underground detectors. The implications are staggering. If dark matter can move in concentrated, high-speed streams, it could rewrite the rules of galaxy formation, particle physics, even our understanding of gravity itself. Some researchers speculate these hurricanes might be cosmic wreckage, shrapnel from ancient collisions between galaxies, hurling dark matter across the void. Others wonder if they're the fingerprints of undiscovered dimensions, warping space in ways we're only beginning to detect. One thing's certain, this isn't just a scientific curiosity. It's a force of nature that could redefine reality as we know it, and it's been hiding in plain sight all along. Next up is something that looks more like a celestial predator than a cosmic cloud. The space jellyfish nebula, a sprawling, tentacled monster of gas and light that drifts through the void with otherworldly grace. Stretching over 200 light-years across, this nebula pulses with an eerie blue glow, its wispy tendrils curling through space like the arms of some ancient deep-sea creature. But here's the twist. Unlike most nebulae which are sculpted by the gentle winds of dying stars, this one crackles with energy that scientists still can't fully explain. What makes this cosmic jellyfish so baffling? For starters, its structure is a total anomaly. Typical nebulae like the famous Orion or Crab Nebula form symmetrical, bubble-like shapes blown outward by stellar explosions or radiation pressure. But the space jellyfish, its filaments twist and knot in chaotic, asymmetrical loops as if something or someone reached into the cosmos and gave it a violent stir. Even stranger, it's not just glowing from starlight. X-ray telescopes reveal pockets of superheated gas embedded in its tendrils, suggesting forces at work far more intense than the gentle push of stellar winds. One leading theory points to a runaway black hole, a rogue behemoth that may have shot through the nebula like a bullet, dragging streams of gas in its wake and leaving this twisted wreckage behind. Others speculate it's the aftermath of a hypervelocity star, a stellar speedster rocketing through space so fast it shredded the surrounding gas into these eerie, flowing ribbons. But the wildest idea, that we're seeing the fingerprints of dark matter. Some researchers suggest invisible particles could be interacting with the nebula's gas in ways we've never observed, creating these bizarre, undulating shapes. Here's why it matters. Nebulae are cosmic laboratories, showing us how matter behaves under extreme conditions. If this one defies the rulebook, it could mean our understanding of gas dynamics, magnetic fields, even the life cycles of galaxies is missing a crucial page. And for stargazers, it's a haunting reminder. The universe isn't just vast, it's alive with mysteries swirling right in front of us, waiting to be unraveled. Now, let's turn our attention to one of the most haunting discoveries in modern astronomy, a black hole that doesn't just consume light but actually sings. Nestled 250 million light-years away in the heart of the Perseus galaxy cluster, this supermassive behemoth has been humming a deep, resonant note across the cosmos for billions of years. And here's what's truly mind-blowing. Astronomers have not only detected these sound waves, they've translated them into something human ears can hear. The first clue came from NASA's Chandra X-ray Observatory, which detected ripples in the hot gas surrounding the black hole. At first glance, they looked like ordinary pressure waves until scientists realized their frequency was staggeringly low, vibrating once every 10 million years. Converted into musical terms, that's a B-flat 57 octaves below middle C, a pitch so deep it's beyond the range of human hearing, but when sped up by several quadrillion times. The result is an unearthly drone, a cosmic bass note echoing through the void like the hum of a distant, unstoppable engine. So how does a black hole, an object famous for trapping even sound itself, produce these vibrations? The answer lies in its appetite. As the black hole devours surrounding gas, it doesn't do so quietly. Turbulence in the infalling material generates pressure waves that ripple outward through the superheated plasma of the galaxy cluster, much like sound waves travel through air. But unlike earthbound sounds, which fade quickly, these waves persist for eons, trapped in the dense medium like echoes in a cathedral. Over time, they've carved vast, concentric rings into the cluster's gas, visible in X-rays like grooves on a cosmic record. What makes this discovery revolutionary isn't just the novelty of a singing black hole. These sound waves are heating the surrounding gas, preventing it from cooling and forming new stars. That means this eerie hum isn't just background noise, it's actively shaping the evolution of an entire galaxy cluster, putting a brake on star formation on an unimaginable scale. Some scientists even speculate that similar processes could explain why certain regions of the universe are mysteriously devoid of young stars, as if something or someone has hit the cosmic mute button. Yet the biggest mystery remains why this particular black hole sings so loudly. Most supermassive black holes are relatively quiet, their feasts producing only faint whispers. But this one's voice carries across intergalactic space, suggesting something extraordinary about its environment or feeding habits. Could it be gorging on an unusually dense cloud of gas? Or is its song amplified by the unique properties of the Perseus cluster's atmosphere? Either way, one thing's clear: black holes aren't the silent monsters we once imagined. They're composers in the dark, conducting symphonies we're only just learning to hear. Imagine two worlds so close together they breathe as one. A pair of exoplanets locked in a cosmic dance so intimate their atmospheres mingle like shared breath between lovers. This isn't science fiction, it's the reality of K2 181b and C, twin planets orbiting a star 500 light-years away with a bond unlike anything in our solar system. Separated by just 1.6 million kilometers closer than Earth is to the Moon, these worlds whirl around each other every 38 hours, their gravitational embrace so tight that hydrogen and helium stream between them in a perpetual, swirling exchange. What makes this discovery so revolutionary? In our own cosmic neighborhood, planets are distant, solitary giants, each sealed in its own atmospheric bubble. Even Venus and Earth, siblings in size, are separated by a yawning chasm of space. But here, the rules are rewritten. Telescopes detected helium trailing from one planet to the other like a celestial bridge, a phenomenon never before observed. It's as if Jupiter and Saturn were pressed cheek to cheek, their storms and gases bleeding into one another, a scenario so extreme it forces us to rethink how planetary systems can evolve. Could such closeness foster life? The conditions are as bizarre as they are breathtaking. One planet, bathed in constant starlight, bakes at nearly 1,000 degrees Celsius, its atmosphere evaporating under the heat. The other, forever turned away, exists in perpetual shadow, its cooler temperatures condensing those escaping gases into a hazy, global shroud. Yet in the twilight zone where their atmospheres collide, scientists speculate about a narrow band of stability, a region where temperatures might allow liquid water, and where organic molecules carried on the interstellar wind between worlds could find a foothold. It's a tantalizing thought, life not on one planet but across two, hopping the atmospheric bridge between them like spores on a breeze. The implications ripple far beyond these twins. If planets can share atmospheres, what else might they share? Microbial life, chemical precursors to biology. Some theorists even suggest such systems could act as interstellar way stations, where life spreads not just across a single world, but between adjacent ones, accelerating the pace of cosmic evolution. And here's the kicker. Astronomers now suspect such pairs might be common in the universe, hiding in plain sight around red dwarf stars, their tight orbits making them invisible to older detection methods. Yet the mystery deepens when we ask, how did they get so close? Most planetary formation models can't explain it. Planets this size should have collided or been flung apart long ago. One daring hypothesis proposes they formed farther apart, migrating inward over eons until their dance became this intimate embrace. Another suggests they're survivors of a violent past, the last members of a larger family now lost to cosmic chaos. Whatever the answer, one thing's clear: the universe has a flair for the dramatic, crafting worlds that defy our textbooks and ignite our imagination. Now contrast this with our own solar system, where planets are islands, isolated and self-contained. Earth's atmosphere is ours alone, a fragile bubble untouched by neighboring worlds. But K2-181's twins whisper a provocative question. What if we're the odd ones? What if tightly knit planetary systems are the norm and our solitary existence the exception? It's a humbling thought and a reminder that every time we peer into the cosmos, it doesn't just show us new worlds. It holds up a mirror, revealing how little we truly understand. Deep in the constellation of Cancer, a world exists where the skies might rain liquid metal and the surface glitters with crystallized carbon. Welcome to 55 Cancri E, the diamond planet with a metal sky. This exoplanet, twice Earth's size but 8 times its mass, orbits so close to its star that a single year lasts just 18 hours. Surface temperatures here soar beyond 2,000 degrees Celsius, hot enough to vaporize rock and forge conditions so extreme they defy everything we know about planetary chemistry. What makes this world truly alien isn't just the heat, it's the sheer abundance of carbon. Unlike Earth's silica-rich crust, 55 Cancri is likely packed with graphite and diamond, forming a crust that could be miles deep in crystallized gemstones. But the real spectacle happens above the surface. Recent studies suggest its atmosphere might be laced with vaporized metals like silicon carbide and iron, condensing into droplets that fall as metallic rain. Picture a thunderstorm where the droplets aren't water but molten titanium, sizzling through neon-colored skies before pooling in shimmering metallic lakes. How does such a hellscape even form? The answer lies in its birth. Most rocky planets, including Earth, coalesce from debris rich in oxygen and silicon. But this world's parent star has unusually high carbon levels, meaning the building blocks of 55 Cancri were more akin to cosmic charcoal than Earth's dusty ingredients. Under the crushing pressure of its dense interior, carbon atoms could have been squeezed into diamond structures, while lighter elements like nitrogen and oxygen common in our atmosphere were baked away, leaving behind heavier metals. Here's where it gets stranger. Some models suggest the planet might be tidally locked, with one side permanently facing its star. The day side, scorched by relentless radiation, could host rivers of molten silicon, while the night side, colder but still hellishly hot, might trap condensed metal vapors in a perpetual glowing haze. This stark contrast could create hurricane-force winds as temperature differences send supersonic gusts racing across the surface, carrying with them flecks of diamond dust like a surreal interstellar sandstorm. Yet the biggest mystery isn't just what 55 Cancri is made of, it's how such a planet survives at all. At this proximity to its star, most worlds would be stripped bare by stellar winds, their atmospheres blown into space like smoke in a hurricane. But somehow this one endures. One theory proposes its metallic atmosphere acts as a shield, absorbing radiation and re-radiating it back into space, creating a bizarre equilibrium. Another suggests the planet might be the corpse of a gas giant, its outer layers vaporized long ago, leaving behind a dense metallic core cloaked in exotic vapors. For astronomers, this isn't just a curiosity, it's a laboratory for the impossible. By studying how materials behave under such extreme pressure and heat, we're glimpsing conditions that might exist inside super-Earths or even rogue planets adrift between stars. And for dreamers, it's a reminder that the universe's creativity knows no bounds. Who needs science fiction when reality offers skies that rain metal and landscapes paved in diamonds? Yet beneath the spectacle lies a sobering truth. For all its glitter, 55 Cancri is a monument to cosmic extremes, a world where the very air would dissolve your bones, and the ground beneath your feet is worth more than empires, yet utterly worthless to life as we know it. Now let's shift our gaze to a cosmic rebel, a galaxy that doesn't just bend the rules, it throws them out entirely. Meet NGC 1052DF2, a ghostly, see-through galaxy that astronomers discovered has virtually no dark matter. That's like finding a car without an engine, a sandwich without bread. It defies everything we thought we knew about how galaxies work. Dark matter, that mysterious substance we can't see but know exists because of its gravitational pull, has long been considered the cosmic glue holding galaxies together. Without it, galaxies shouldn't have enough mass to stay intact. Their stars would fly apart like a shattered disco ball. Yet here's NGC 1052DF2, floating serenely in space, its stars moving at a leisurely pace, no frantic orbital speeds, no signs of the invisible scaffolding we've come to expect. So where did its dark matter go? One theory suggests it was violently stripped away. Picture this, the galaxy might have once been normal, but as it drifted through a dense cluster, gravitational tides could have ripped its dark matter loose, leaving behind a skeleton of stars. Others propose it never had much to begin with. Perhaps it formed differently, a rogue collection of stars born from gas too thin to trap dark matter, like a sandcastle built without cement. But the wildest idea, that dark matter isn't what we think it is. Some physicists argue this galaxy might be evidence for modified gravity theories, where the rules of attraction change on cosmic scales, eliminating the need for dark matter entirely. If true, it would upend decades of astrophysics, rewriting the book on how the universe structures itself. Yet skeptics aren't convinced. They point to measurement errors or hidden complexities. Maybe the dark matter is there, just hiding in a form we can't detect. Or perhaps NGC 1052DF2 is a cosmic fluke, a statistical oddity in a universe that thrives on diversity. One thing's certain, this galaxy isn't just a curiosity. It's a cosmic thorn in the side of established theories, forcing us to question whether dark matter is universal or if the universe has more tricks up its sleeve. And that's the beauty of discovery. Sometimes the most profound truths come from the things that shouldn't exist at all. Stars aren't supposed to cheat death. When they reach the end of their lives, they go out with a bang, a supernova so violent it can outshine entire galaxies before fading into oblivion. But in 2014, astronomers witnessed something that shouldn't exist, a star that exploded and then kept right on shining. Meet IPTF-14 HLS, the cosmic zombie that refused to die. This wasn't just a minor flare-up. The star detonated with the force of a typical supernova, blasting its outer layers into space in a cataclysmic fireball. Yet months later, when the light should have dimmed to nothing, it flared back to life not once but multiple times, pulsing with erratic bursts of energy like a heartbeat from beyond the grave. Telescopes caught it glowing defiantly for over 600 days, a stellar phoenix rising from its own ashes again and again. So how does a star survive its own funeral? The leading theory is as bizarre as the star itself. Normally, when massive stars go supernova, their cores collapse into black holes or neutron stars, while the rest vaporizes in the explosion. But IPTF-14 HLS might have been part of a binary system, orbiting a companion star that wasn't ready to let go. As the doomed star exploded, its surviving twin could have funneled fresh hydrogen into the wreckage, reigniting nuclear fusion in the remnants like pouring gasoline on embers. The result, a star caught between life and death, cannibalizing its partner's material to fuel its own resurrection. Here's where it gets weirder. Most supernova remnants cool as they expand, but this one's temperature spiked unpredictably, sometimes doubling in weeks, as if an invisible hand kept turning up the thermostat. Spectra revealed swirling layers of calcium, titanium, and iron, elements normally buried deep in a star's core, now churned to the surface by forces no model predicted. It's like dissecting a corpse only to find its organs rearranged, still pulsing with life. But the real shock came when researchers dug into older images. Hidden in decade-old data, they found the star had suffered smaller explosions years before the big event, stellar seizures that might have ejected shells of gas into space. When the final supernova hit, its shockwaves could have slammed into these pre-existing debris fields, creating fireworks of rebounding energy. Imagine tossing a lit match into a trail of gunpowder you didn't know was there suddenly. The explosion isn't a single event, but a chain reaction of surprises. What does this mean for astrophysics? For starters, it throws a wrench into our tidy classifications of stellar deaths. Textbooks describe supernova as endpoints, but this zombie star suggests some might be checkpoints, pauses in a longer, stranger life cycle we're only beginning to map. Some theorists now wonder if other failed supernovae have been hiding in plain sight, masquerading as ordinary stars after their supposed demise. Others speculate these events could solve long-standing mysteries, like the origins of weirdly heavy neutron stars or the sources of certain cosmic rays. And then there's the existential question: if stars can fake their deaths, what else might we be missing? The universe has just shown us its penchant for theatrical encores, so next time you gaze at the night sky, remember, some of those twinkling lights might not be stars at all, but ghosts wearing starlight as a disguise. Most cosmic signals come and go like static on a radio, random, unpredictable blips from the depths of space. But in 2020, astronomers caught something different, a fast radio burst that didn't just repeat, it kept perfect time. Every 16 days, like clockwork, this pulse of energy flashed across the universe, arriving with a rhythm so precise it felt almost intentional. Fast radio bursts, or FRB, are among the most energetic phenomena in the cosmos. Lasting mere milliseconds, each blast packs as much energy as the sun emits in decades. Most vanish without a trace, leaving scientists scrambling to explain their origins. But this one, dubbed FRB 180916, was different. For 4 days, it would fire off a burst every hour or so, then fall silent for 12 days before starting the cycle all over again. It wasn't just a cosmic hiccup, it was a metronome in the void. So what could possibly keep such perfect time? The leading suspect is a neutron star, specifically a highly magnetized type called a magnetar. These dense stellar corpses spin rapidly, sending out beams of radiation like interstellar lighthouses. If one of these beams happened to align with Earth periodically, say, due to a wobble in its rotation or an orbiting companion, it might explain the 16-day rhythm. Picture a spinning top with a slight tilt, its flickering light hitting your eyes only at precise intervals. But there's a catch. Magnetars are notoriously unstable, prone to violent eruptions called starquakes that disrupt their rotation. Maintaining such a steady signal for years, as FRB 180916 has done, would require conditions so fine-tuned they border on implausible. Some researchers suggest the answer lies in a binary system, where the neutron stars orbit around another object. Perhaps a black hole or massive star periodically positions it to fire bursts toward us. Others propose a cosmic obstacle course. Dense clouds of debris surrounding the magnetar could act like lenses, focusing its emissions into intermittent flashes visible only when geometry aligns just right. Then there's the wildcard theory, technology. The regularity has inevitably sparked whispers of artificial origins. Could this be a beacon, a deliberate signal from an advanced civilization? While most scientists dismiss this as a last resort explanation, the pattern's precision does raise eyebrows. After all, humans use rhythmic signals like the pulsating beams of lighthouses to communicate across vast distances. Yet the truth might be stranger than any hypothesis. FRB 180916 isn't alone. Other repeating bursts have since been found with cycles of their own, some spanning months. This suggests an entire family of cosmic timekeepers, each with its own rhythm, ticking away in the dark. And that's the real mystery. Why do these bursts repeat at all? Supernova don't explode in cycles. Black holes don't snack on matter with a schedule. Whatever's behind these signals, it's revealing a new class of celestial behavior, one that defies our current playbook. For now, the 16-day enigma remains unsolved, a reminder that even in the era of megatelescopes and AI-driven astronomy, the universe still holds cards close to its chest. Every time we decode one signal, another begins its cryptic transmission, as if space itself is teaching us patience. One thing's certain: when the next cycle begins, the world's telescopes will be listening, waiting for the cosmos to whisper its secrets again. Drifting alone through the icy darkness between stars, a planet with no sun paints the void with ghostly light. This rogue world, known as SIMP J0 13656+0943, doesn't orbit any star. It's a cosmic nomad, untethered and adrift. Yet despite its solitude, it puts on a light show that rivals Earth's northern lights, glowing with auroras 1,000,000 times more powerful than our own. How does a world without solar wind, the charged particles that normally trigger such displays, create such brilliance in the abyss? The answer lies in its turbulent heart. Unlike Earth, where auroras stem from solar particles colliding with our magnetic field, this rogue planet generates its own chaos. Imagine a Jupiter-sized world, its interior still seething with heat from formation, churning molten metals deep beneath a smothering atmosphere of hydrogen. This dynamo effect creates a magnetic field so intense it crackles with energy, whipping charged particles into frenzied motion. As these particles spiral along magnetic field lines, they smash into atmospheric gases, igniting shimmering curtains of light that dance across its eternal night. What makes this discovery revolutionary isn't just the absence of a star. It's the sheer scale of the phenomenon. Earth's auroras stretch hundreds of kilometers. This planet could engulf it whole, wrapping the world in a luminous shroud visible light years away. Telescopes detected the telltale radio emissions of these auroras, a signature so strong it betrayed the planet's presence despite its cold, starless exile. But here's the twist. Rogue planets were thought to be dark, frozen relics, their magnetic fields faded with time. Yet this one defies expectations, its auroras proving it's anything but dormant. Some scientists speculate it might be young, still burning with the heat of its violent birth. Others wonder if tidal forces from a hidden moon or even interactions with interstellar plasma could be juicing its magnetic engine. The implications ripple far beyond this lonely world. If free-floating planets can host such dazzling displays, how many more might be lurking in the dark, their unseen auroras painting the cosmos? Could some even sustain warm, layered atmospheres beneath those glowing skies, creating pockets of habitability in the void? It's a tantalizing thought that the greatest light shows might not happen around stars, but in the deepest dark where orphaned worlds turn their isolation into art. Yet the mystery runs deeper. Without a star's energy, how long can these auroras last? Centuries, millennia? However fleeting, they're a beacon, proof that even in the coldest corners of the universe, nature finds a way to shine. Among the countless nebulae scattered across the cosmos, few capture the imagination like the Twin Jet Nebula, nicknamed the Butterfly for its breathtaking, wing-like symmetry. This celestial masterpiece stretches over 2 light-years wide, its vibrant lobes of gas unfurling from a dying star system at its heart. But what gives this cosmic insect its delicate shape? The answer lies in a violent dance of stellar winds. At the nebula's core, not one but 2 stars orbit each other in a tight embrace, their combined outflows carving the surrounding gas into those iconic wings. The primary star, a fading red giant, sheds its outer layers in slow, dense waves, while its smaller companion, a white dwarf, blasts these ejections with faster, hotter winds. The result is a sculpting process as precise as it is destructive, where contrasting streams of particles collide and curve, etching the nebula's ethereal contours into space. Now shift your gaze to the Windsurfer Nebula, an interstellar marvel that looks less like a butterfly and more like a kite caught in a hurricane. Unlike the Twin Jet's balanced wings, this structure boasts a lopsided, almost windswept profile, with a prominent sail of glowing gas trailing behind its central star. The key to its asymmetry, motion. While the butterfly's shaping stars sit relatively still, the Windsurfer's progenitor is racing through space at over 200,000 kilometers per hour, so fast it's leaving a bow shock in the interstellar medium, like a speedboat churning up water. Radiation from the dying star then illuminates this wake, creating the illusion of a cosmic surfer riding its own stellar breeze. What unites these 2 nebulae, despite their differing forms, is the artistry of physics. Both are planetary nebulae, the final exhalations of sun-like stars, yet their structures tell wildly different stories about their creators' lives. The butterfly's symmetry hints at a binary system's orderly chaos, where dual outflows interact like dueling paintbrushes on a galactic canvas. The Windsurfer's wild asymmetry, meanwhile, speaks to solitary velocity, its shape forged by the relentless push of its journey through space. One is a waltz, the other a sprint, both turning stellar death into fleeting beauty. Yet there's a deeper lesson here. These nebulae aren't just pretty accidents, they're time capsules. By studying their shapes, astronomers can reconstruct the lives and deaths of their central stars. The butterfly's precise wings, for instance, suggest its binary stars orbit every 100 years or so, their gravitational tango directing the outflowing gas. The windsurfer's chaotic sail, conversely, implies its star was likely kicked into motion by a past encounter, perhaps a near collision with another star or the gravitational slingshot of a black hole. Every curve and ripple encodes millennia of history waiting to be decoded, and then there's the ephemeral nature of it all. These nebulae will vanish in mere tens of thousands of years, a blink in cosmic time, their gas dissipating into the interstellar void. What we're witnessing isn't just stellar death, but a fleeting moment of metamorphosis where the ordinary becomes extraordinary. The butterfly's wings will fade, the windsurfer's sail will tear. But for now, they glow reminders that even in the vast, uncaring universe, destruction can birth art beyond human imagination. Hidden beneath miles of ice, churning in perpetual darkness, lies an ocean that defies all expectations, not on Europa or Enceladus, but on a moon so distant we don't even know its name. Orbiting a gas giant 20 times the mass of Jupiter, this enigmatic exomoon might just be the most promising candidate for alien life ever discovered. What sets it apart isn't just the presence of water. It's the sheer scale of its subsurface sea, a sprawling liquid abyss larger than all of Earth's oceans combined, wrapped in an icy shell thicker than the Grand Canyon is deep. The first clue came from subtle wobbles in the parent planet's orbit, betraying the moon's gravitational tug. But when astronomers analyzed the system's reflected light, they found something extraordinary, spectral signatures hinting at geysers. Just like Saturn's moon Enceladus, this distant world seems to be spewing plumes of water vapor through cracks in its frozen crust, a telltale sign of hydrothermal activity below. Yet here's where the similarities end. Unlike our solar system's icy moons, which rely on tidal friction from their gas giants for heat, this exomoon shouldn't have enough energy to keep its ocean liquid. Its host planet orbits too far from its star for sunlight to make a difference, and tidal forces alone can't explain the violence of those eruptions. So what's cooking this alien ocean? The answer might lie in radioactive decay. Heavy elements like thorium and uranium, forged in ancient supernova, could be concentrated in the moon's rocky core, their slow disintegration providing a steady pulse of warmth. Picture a natural nuclear reactor buried under ice, its gentle heat preventing the ocean from freezing solid over billions of years. Alternatively, the moon's orbit might trace an exaggerated ellipse, creating tidal flexing intense enough to melt ice through sheer gravitational kneading. Either scenario paints a portrait of resilience, a world that's found a way to sustain liquid water in one of the harshest environments imaginable. Now, let's talk about that elephant in the room, life. Earth has taught us that where there's liquid water and energy, life finds a way from scalding hydrothermal vents to Antarctic glaciers. But this exomoon's ocean isn't just habitable, it's a paradise by microbial standards. Protected from cosmic radiation by its ice shield and powered by geothermal or radioactive energy, it could host ecosystems as rich as our own deep-sea vent communities. Some astrobiologists speculate that without UV radiation breaking down complex molecules, organic chemistry here might have had a quieter, more stable environment to evolve, potentially leading to life forms unlike anything we've imagined. The wild card, salt. If this ocean is briny like Europa's, it could remain liquid at far lower temperatures, with antifreeze compounds like ammonia or magnesium sulfate preventing total freezing. But if it's fresh, as some models suggest, it might resemble Earth's primordial seas, a blank slate for life's experiments. Then there's the ice itself. Fractured by gravitational stresses, it could form a porous ceiling, allowing organic material to circulate between surface and depths like a cosmic conveyor belt. Yet the real showstopper is time. While Mars' oceans dried up and Europa's may be geologically young, this exomoon's ocean could have persisted for most of the universe's history, an uninterrupted 10 billion-year incubator. Imagine what evolution could craft in that span. Intelligent cephalopods, bioluminescent forests clinging to underwater ridges, or perhaps something so alien we lack the vocabulary to describe it. Of course, there are hurdles. That icy crust isn't just a shield, it's a prison, locking away any potential biosignatures from our telescopes. Future missions might need to sample those geyser plumes directly or use gravitational wave detectors to map the ocean's currents. Until then, this nameless moon remains a tantalizing what-if, a reminder that the universe's most promising real estate might not be planets at all, but the frozen moons hiding secrets in their depths. And who knows, the first proof we're not alone in the cosmos might not come from a distant Earth twin, but from a humble moon's dark, swirling ocean waiting patiently to be discovered. Picture the universe not as a scattering of isolated galaxies, but as a vast, intricate spiderweb, one spun not from silk, but from galaxies themselves, stretching across unimaginable distances in delicate, luminous threads. This is the cosmic web, the hidden skeleton of our universe, and recently, astronomers spotted one of its most spectacular filaments, a tendril of galaxies over 500 million light-years long, weaving through the void like a celestial river. What makes this structure so extraordinary isn't just its scale, it's what holds it together. The galaxies in this filament are mere waypoints, tiny beads strung along an invisible highway of dark matter. Scientists believe these threads form the universe's ultimate scaffolding with dark matter, that mysterious, gravity-producing substance acting as the unseen loom on which the web is woven. In the early universe, slight density fluctuations in dark matter created gravitational wells, pulling in ordinary matter like gas and dust. Over billions of years, these accumulations grew into the galaxies we see today, all while remaining tethered to the dark matter filaments like pearls on a string. Here's where it gets eerie. This particular filament, located in the Pisces constellation, isn't just a passive structure, it's a cosmic conveyor belt. Observations show galaxies sliding along its length, drawn toward dense knots where multiple filaments intersect. These knots, known as galaxy clusters, are the universe's megacities, bustling with hundreds or even thousands of galaxies. The filament acts as a feeding tube funneling galaxies and the gas needed to form new stars into these crowded hubs, but the real marvel is how we detected it. Since dark matter doesn't emit light, astronomers had to use a clever trick. They mapped the filament by studying the way its gravity distorts light from background galaxies, a phenomenon called weak gravitational lensing. It's like spotting an invisible wire by watching how it bends the view behind it. Combined with the glow of hydrogen gas shimmering between galaxies, this revealed the filament's full, thread-like glory. Why does this matter? The cosmic web isn't just a pretty pattern, it's the blueprint for how everything in the universe fits together. Simulations suggest that nearly 60% of all galaxies reside in filaments, with only a small fraction sitting in isolated voids. This structure also dictates the fate of galaxies. Those in dense clusters age faster, their gas stripped away by violent encounters, while those in quieter filament regions have more time to nurture new stars. Yet mysteries remain. Why do some filaments appear wispy and faint, while others, like this one, gleam with dense galaxy clusters? Some theorists propose that dark matter might clump differently in certain regions, creating variations in the web's thickness. Others wonder if dark energy, the force accelerating the universe's expansion, could be stretching some filaments to the breaking point, leaving them tattered and sparse. One thing's certain, this cosmic web filament is more than a curiosity. It's a window into the universe's architecture, revealing how dark matter's invisible hand shapes everything we see. And as we trace these threads across the void, we're not just mapping the cosmos, we're unraveling the very fabric of reality. Some stars don't just challenge our understanding of the cosmos, they laugh in the face of it. Meet HD 140283, nicknamed the Methuselah star, a celestial elder so ancient it appears to be older than the universe itself. That's right, current estimates peg this unassuming yellow giant at 14.5 billion years old, while the Big Bang supposedly occurred a mere 13.8 billion years ago. It's like finding a birth certificate that predates your own parents. How does such a paradox even exist? The answer lies in the delicate art of cosmic archaeology. To date stars, astronomers rely on two key clues: their composition and their position on the Hertzsprung-Russell diagram, which maps stellar brightness against temperature. Methuselah's composition is bizarrely metal-poor, meaning it formed from nearly primordial gas, untouched by the heavier elements forged in later supernova. Its position suggests it burned through its hydrogen fuel eons ago, transitioning into the subgiant phase, a process that typically takes billions of years. But here's where things get messy. Measuring stellar ages isn't like counting tree rings. It's more like guessing a person's lifespan by their posture and diet. Early calculations might have overestimated Methuselah's age due to uncertainties in its distance. Revised parallax measurements from the Gaia satellite placed it slightly farther away, which dimmed its apparent brightness and in turn suggested it might be younger. Yet even with these adjustments, the star stubbornly clings to an age uncomfortably close to the universe's, highlighting cracks in our cosmic timeline. One radical explanation involves tweaking the universe's expansion rate. If the Hubble constant, the value describing how fast the cosmos expands, is slightly off, it could mean the universe is actually older than we think. Alternatively, Methuselah might have been born in a now-vanished dwarf galaxy, where unique conditions accelerated its evolution, making it appear older than it is. The wildest theory, that the star's primordial lithium levels hint at physics beyond the standard model, perhaps interactions with dark matter that altered its internal clock. Whatever the truth, Methuselah isn't just an anomaly. It's a ticking time bomb in astrophysics, forcing us to question whether we've misread the universe's birth certificate entirely. Deep in the ice beneath the South Pole, a detector the size of a skyscraper caught something extraordinary: a single ghostly particle from the edge of the universe. Not just any particle, but a high-energy neutrino, a nearly massless speck of matter so elusive it can pass through entire planets without a trace. Yet this one left a faint blip of light as it tore through the Antarctic ice, and when astronomers traced its path backward, it led them to a cosmic monster, a blazing blazar 4 billion light-years away, firing jets of radiation directly at Earth. Neutrinos aren't just any cosmic debris, they're nature's stealth bullets, born in the hearts of stars, supernova, and cataclysmic collisions. Unlike light, which can be blocked or scattered, these particles slice through the universe unimpeded, carrying secrets from the most violent events in existence. But there's a catch. Their very elusiveness makes them nearly impossible to trace. For decades, detecting a neutrino source was like finding a single grain of sand on a planet-sized beach. That all changed in 2017 when IceCube, the South Pole's neutrino observatory, spotted this particular particle with energy 1 million times greater than anything produced in earthly particle accelerators. What made this detection revolutionary wasn't just the neutrino itself, it was the eerie precision with which astronomers pinpointed its origin. The moment IceCube sounded the alarm, telescopes across the globe swiveled toward the coordinates. There, in the constellation Orion, sat a blazar dubbed TXS 0506+056, a supermassive black hole spewing twin jets of plasma at nearly light speed. One of those jets happened to be aimed straight at us, acting like a cosmic particle cannon. When the neutrino arrived, scientists realized it wasn't a random fluke. It was a message, a direct telegram from the heart of an active galactic nucleus. This discovery marked a turning point in what's called multi-messenger astronomy, the art of studying the universe not just through light, but by combining signals from neutrinos, gravitational waves, and cosmic rays. Think of it like investigating a crime scene with fingerprints, DNA, and security footage instead of just a blurry photo. For the first time, we had proof that blazars could accelerate not just photons, but neutrinos to outrageous energies, confirming these objects as cosmic particle accelerators on a scale we can barely fathom. But why does this matter beyond scientific bragging rights? Neutrinos carry intel from places light can't escape, like the very edge of a black hole's maw or the core of a collapsing star. By linking them to specific sources, we're essentially decoding the universe's hidden channels of communication. Some researchers now speculate that high-energy neutrinos could be the key to unraveling dark matter's identity, as certain theoretical particles might decay into them. Others suggest they could help map the invisible magnetic highways crisscrossing the cosmos, guiding us through regions too turbulent for light to traverse unscathed. Yet the most tantalizing possibility is what this means for future discoveries. If one blazar can fire neutrinos across 4 billion light-years, how many more messengers might be out there waiting to be matched to their cosmic senders? Every time a neutrino detector pings, it could be a telegram from a colliding neutron star, a quasar's jet, or something even stranger lurking in the void. The universe just handed us a new way to see, not with photons, but with ghostly particles that whisper secrets from the abyss. And that's the beauty of this milestone. It's not an endpoint, but a doorway, one swinging open to reveal a cosmos far more interconnected than we ever dreamed. In a universe teeming with galaxies, where the cosmic web stretches like a crowded metropolis, there exists a place so unsettlingly empty it defies logic, a void spanning nearly 1 billion light-years, where galaxies should be thick as fireflies, but instead, there's nothing. Astronomers call it the KBC void, named after the scientists who mapped its eerie expanse. And it's not just a quiet neighborhood, it's a cosmic ghost town, a bubble of near-perfect nothingness in an otherwise bustling universe. What makes this void so unnerving? Statistically, regions this empty shouldn't exist. The standard model of cosmology predicts matter should be distributed relatively evenly, with small variations forming galaxy clusters and filaments. But the KBC void isn't just a gap, it's a staggering absence, a spherical region where matter is up to 20% sparser than the cosmic average. To put that in perspective, if the universe were a beach, this void would be a stretch of shoreline where the sand simply disappears. So how did this nothingness form? One possibility is that it's a relic of the early universe, a fossilized bubble from the inflationary period when space itself expanded faster than light. Imagine blowing up a balloon with tiny flaws, some patches stretch thinner than others. Over billions of years, those underdense regions could have grown into voids like this one. But here's the twist: the KBC void isn't just empty, it's too empty, challenging even the most generous models of cosmic inflation. That's where the wilder theories come in. Some physicists suggest this void might be the imprint of a collision with another universe, a bruise left behind when our cosmos bumped into a neighboring bubble in the multiverse. Others propose it's evidence of an exotic form of dark energy, one that repels matter more aggressively in certain regions, pushing galaxies away like an invisible hand. The most unsettling idea, that we're seeing a statistical fluke so rare, it's like rolling a die a billion times and landing on one every single time. Yet the plot thickens when you consider our place in this cosmic emptiness. Earth sits uncomfortably close to the void's center, a fact that's either a bizarre coincidence or a clue. If the void's gravity is subtly tugging on the Milky Way, it could explain anomalies in our local motion, hints that this emptiness isn't just passive, but actively shaping the cosmos around it. For astronomers, the KBC void is more than a curiosity, it's a stress test for our understanding of the universe. If voids this large can't exist under current models, does that mean dark energy behaves differently than we thought? Or is there a fundamental flaw in how we measure cosmic distances? Every telescope trained on this nothingness brings us closer to answers, but for now, it remains a silent enigma, a reminder that in a universe full of wonders, sometimes the most profound mysteries are the places where nothing happens at all. Pulsars are nature's precision timekeepers, cosmic lighthouses that spin with such regularity. You could set your watch by their pulses. Most whirl at dizzying speeds, some completing hundreds of rotations every second, their beams slicing through space like a strobe light in the void. But nestled in the constellation Cassiopeia lies a rebel that breaks all the rules, a pulsar spinning just once every 23.5 seconds. Astronomers call it PSR J0250 plus 5854, and its sluggish rhythm isn't just unusual, it's downright impossible according to everything we thought we knew about neutron stars. At first glance, this slow-spinning oddity shouldn't even be detectable. Pulsars emit radio waves from their magnetic poles, and as they rotate, those beams sweep across Earth like the beam of a lighthouse. The slower the spin, the weaker the signal, so by rights, a pulsar this lethargic should have faded into silence eons ago. Yet here it is, pulsing steadily, its radio whispers picked up by telescopes as if taunting astrophysicists with its very existence. The mystery deepens when you consider how pulsars are born. These ultra-dense neutron stars form when massive stars collapse, their cores compressing into a sphere no larger than a city but weighing more than the sun. Conservation of angular momentum means they should start spinning wildly fast, like a figure skater pulling in their arms. Over time, their powerful magnetic fields act like cosmic brakes, sapping their rotational energy and gradually slowing them down. That's textbook physics, except this pulsar didn't get the memo. One leading theory suggests its magnetic field might be freakishly weak. Normally, pulsar magnetic fields decay over millions of years, but J0250 plus 5854's field could have deteriorated far faster, leaving it with less braking power and allowing it to spin longer than expected. It's like a car whose brake pads wore out prematurely, coasting downhill long after it should have stopped. Alternatively, it might have been born unusually slow, perhaps from a star that shed much of its angular momentum before collapsing, a stellar retirement home resident that never had the energy to spin quickly in the first place. Then there's the wild card, magnetar imposters. Some researchers speculate this pulsar could be the faded remnant of a magnetar, a neutron star with an ultra-strong magnetic field. If its field decayed rapidly after birth, it might have transitioned from a magnetar's violent youth to this sluggish middle age, skipping the typical pulsar phase altogether. Imagine a rock star who burned out after one wild album and now lives quietly in the suburbs, still technically a musician but nothing like their former self. Whatever the explanation, this pulsar forces us to rewrite the neutron star playbook. Its very existence hints at hidden diversity in stellar evolution, suggesting that some neutron stars might take paths we've never imagined. And here's the kicker: if one of these slowpokes exists, there could be thousands more lurking undetected, their faint pulses lost in the cosmic background noise. Future radio telescopes might uncover a whole population of these cosmic tortoises, rewriting our understanding of how stars live, die, and spin their way through the universe. But the real puzzle isn't just how this pulsar spins so slowly, it's why it hasn't faded into oblivion. Most slow pulsars should have crossed the death line, a theoretical threshold where their magnetic fields can no longer generate detectable radio emissions. Yet J0250 plus 5854 lingers, pulsing defiantly, as if nature itself is reminding us that the universe's rulebook still has blank pages waiting to be filled. For astronomers, that's not just a mystery, it's an invitation to keep searching, because the cosmos always has another surprise up its sleeve. Tabby's star refuses to play by the rules. Officially known as KIC 8462852, this bizarre flickering sun burst into fame in 2015 when astronomers noticed its light curving in ways no ordinary star should. Most stars dim slightly when planets pass in front of them, predictable, rhythmic dips in brightness, but Tabby's star, it would plummet by up to 22% at random intervals, as if something colossal and misshapen kept drifting across its face. The internet erupted with theories, from swarms of comets to, yes, alien megastructures, a Dyson sphere under construction, perhaps built by an advanced civilization to harness the star's energy. Fast forward to today, and the mystery has only deepened. Recent observations confirm the star's dimming isn't just erratic, it's wavelength dependent, meaning some colors of light fade more than others. That's a smoking gun pointing toward dust, not solid megastructures. Dust particles scatter blue light more than red, which matches the star's behavior. But don't pack up the extraterrestrial hypothesis just yet. This isn't ordinary dust. It's microfine with grains smaller than cigarette smoke, and it's unevenly distributed in clumps that orbit the star in no discernible pattern. One leading theory suggests a cosmic catastrophe, a shattered moon or collision between planets could have littered the system with this bizarre debris. Imagine two Mars-sized worlds smashing together, their pulverized remains swirling into a chaotic, opaque haze. Another idea posits that the star itself is to blame. Unlike our Sun, Tabby's star is an F-type, hotter and more massive, which means its intense radiation could be evaporating a nearby ice giant, stripping away its atmosphere to create a trailing cloud of vapor and dust. But here's the twist: even the dust explanation leaves gaps. Some dimming events last for days, others for weeks, with no clear rhythm. If it's just orbiting debris, why doesn't it follow predictable cycles? And why does the star's overall brightness also decline by nearly 1% per year, as if it's slowly being veiled? A few researchers still quietly argue for artificial origins, suggesting the dust could be a byproduct of massive construction like interstellar sawdust from a project too vast for us to comprehend. The truth: Tabby's star is a mirror reflecting back our own biases. When we first saw its flickers, we glimpsed megastructures because we're a species that builds. Now, as dust seems more likely, we're forced to confront the universe's capacity for natural chaos. Maybe the answer isn't one or the other, but both, a reminder that the cosmos thrives on complexity, where even the simplest explanations unravel into new questions. Every time we point a telescope at this star, it teaches us the same lesson. The universe doesn't care what we expect, it just keeps surprising us. Black holes are cosmic vacuum cleaners, right? At least that's the image we've all been sold. Unstoppable monsters that devour everything in their path, leaving nothing behind, not even light. But in 2022, astronomers witnessed something that shattered that stereotype. A supermassive black hole, after tearing apart a hapless star in a violent event called a tidal disruption event, did something utterly unexpected. It burped. 3 years after its stellar meal, this beast in galaxy SDSJ0738+2016 unleashed a colossal jet of plasma, as if suddenly remembering it had forgotten to digest properly. This wasn't just a hiccup. The jet blasted outward at half the speed of light, a belch of energy so fierce it lit up radio telescopes across the globe. The delay made no sense. Black holes aren't supposed to take years to process their food. Normally, when a star gets too close, it's shredded into a swirling disk of debris, and that material should either vanish beyond the event horizon or get funneled into jets immediately. But 3 years, that's like eating a steak and waiting half a decade before feeling full. So what caused the hold-up? One theory points to the black hole's digestion, or lack thereof. Imagine the star's remains didn't spiral inward right away. Instead, they might have pooled in a temporary holding pattern, a cosmic stomach of magnetized gas. Over time, turbulence or magnetic instabilities could have triggered a sudden collapse, dumping that stored material onto the black hole all at once. The result, a delayed but devastating energy surge, as if the black hole's engine finally turned over after a long, stubborn crank. Another idea involves the black hole's spin. If it's rotating sluggishly, its accretion process might be inefficient, like a broken conveyor belt sporadically dropping crumbs into the abyss. Suddenly, a shift in the magnetic field could snap things into alignment, launching the pent-up plasma in a delayed outburst. Or perhaps the star's debris fragmented unevenly, with some chunks taking years to spiral close enough to ignite the jet. But here's the real kicker. This burp isn't just a curiosity, it's a clue to one of astrophysics' biggest puzzles. We've long assumed black holes operate on short timescales, with jets flaring up within weeks or months of a meal. If they can hold onto material for years before erupting, it means our models of accretion physics, how black holes feed and grow, are missing something fundamental. Suddenly, every tidal disruption event we've observed might need revisiting. Could other black holes have hidden reservoirs of half-digested stars waiting to erupt? And if so, does that mean we've underestimated their role in shaping galaxies? Think about it. Active galactic nuclei, supermassive black holes with jets, are known to regulate star formation by blasting away nearby gas. If these outbursts can happen years after the fact, it suggests black holes might influence their galaxies in delayed, unpredictable bursts, like a time bomb with no countdown. That could explain why some galaxies flicker with sudden bursts of activity long after quiet periods. Yet the most tantalizing question remains: how many more of these delayed eruptions are out there, masquerading as unrelated cosmic events? Astronomers are now scouring old data for similar cases, wondering if what we once called random flares might actually be the belated echoes of forgotten stellar feasts. It's a humbling reminder black holes don't just defy space and time. They play by their own rules, and we're only just beginning to decode them. Black holes aren't just cosmic vacuum cleaners, they can be dancers too. Take J1655, a black hole locked in a gravitational tango so chaotic it defies all expectations. Nestled in a distant galaxy, this supermassive beast doesn't orbit neatly around its partner. Instead, it lurches through space like a drunkard stumbling through a crowd, its path erratic and unpredictable. Normally, black holes in binary systems follow smooth, elliptical orbits, but this one's trajectory looks like it was drawn by a toddler with a crayon. The culprit, a third black hole lurking just outside the system, whose gravitational nudges send J1655 into a frenzied wobble, as if the universe itself is playing a game of cosmic pinball. Now shift your gaze to a black hole that doesn't just dance, it does gymnastics. In 2021, astronomers spotted a rare phenomenon in galaxy 126732, a supermassive black hole whose accretion disk, the swirling ring of doomed matter, had flipped upside down. That's right, this cosmic monster isn't just feeding, it's performing a backflip mid-meal. The leading theory suggests a smaller black hole collided with the disk at a steep angle, like a bullet striking a vinyl record, sending it into a dizzying spin reversal. The result, a disk that now whirls perpendicular to its original plane, spewing jets of radiation in wild, spiraling directions. What makes these discoveries revolutionary isn't just the spectacle, it's what they reveal about gravitational waves. Every lurch, every flip sends ripples through spacetime itself, distortions so subtle they're detectable only by instruments like LIGO and Virgo. J1655's erratic dance, for instance, produces gravitational waves with jagged, unpredictable patterns, unlike the clean sine waves of typical black hole mergers. These irregularities could help us map the hidden architecture of galactic centers, exposing the presence of unseen companions or warped spacetime. Meanwhile, the backflipping black hole's disk generates waves with a unique polarization. a cosmic fingerprint that might reveal how often these violent reorientations occur across the universe. Yet the implications run deeper. If black holes can flip their disks so dramatically, it could explain why some galaxies' jets point in bizarre directions, seemingly defying physics. These aren't just cosmic quirks, they're clues to the turbulent lives of black holes, reminding us that even the universe's most powerful objects aren't immune to a little chaos. And for gravitational wave hunters, each oddity is a new dialect in spacetime's hidden language, one we're only just learning to translate. Most of the universe is invisible. Dark matter outnumbers ordinary matter 5 to 1, but we rarely get to see that hidden reality so starkly as with Dragonfly 44. This ghostly galaxy, floating in the Coma Cluster 300 million light-years away, shouldn't exist by traditional standards. It emits barely any light, less than 1% of the Milky Way's glow, yet it weighs as much as 1 trillion suns. The only reason we found it, its colossal mass bends the light of background galaxies like a cosmic magnifying glass, revealing its presence through gravitational lensing. Without that telltale distortion, we'd have no idea it was there at all. What makes Dragonfly 44 so unsettling is its composition, almost entirely dark matter. Unlike typical galaxies where stars and gas dominate, this one's visible matter is a mere sprinkle, just one star for every 100 the Milky Way has. The rest, an unseen ocean of dark matter, so dense it warps space-time around it like a lead weight on a trampoline. Imagine a city where 99% of the buildings are cloaked in fog, leaving only a handful of flickering street lamps to hint at the metropolis beneath. That's Dragonfly 44, a shadowy giant hiding in plain sight. Here's where it gets eerie. If one such galaxy exists, how many more are out there, invisible to our telescopes? Current estimates suggest the universe could harbor thousands of these dark galaxies, drifting like phantom ships through cosmic voids. Some might be failed galaxies that never gathered enough gas to spark star formation. Others could be the corpses of ancient systems, their stars stripped away by collisions, leaving only their dark matter skeletons behind, the most unsettling possibility. That these ghosts aren't outliers, they're the norm, outnumbering luminous galaxies 10 to 1. We just haven't seen them because, well, they're invisible. The discovery forces us to rethink how galaxies form. Standard models assume dark matter halos act as scaffolds, pulling in gas that condenses into stars. But what if some halos never attract enough gas or lose it to cosmic winds? Dragonfly 44 suggests dark matter can exist in vast, isolated clumps, untethered to the stellar nurseries we associate with galaxies. It's like finding a skeleton without a body, proof that the scaffolding can stand alone. Now consider the implications for dark matter itself. If these galaxies are truly 99% dark, their gravitational lensing could help us map the substance's distribution with unprecedented precision. Some theorists even speculate they might harbor exotic dark matter particles, clumping in ways that defy current theories. Others wonder if they're the key to solving the missing satellite problem, the puzzling shortage of small galaxies our models predict should orbit larger ones. Perhaps they're not missing at all, perhaps they're just dark, yet the greatest mystery isn't what these galaxies are, it's what they mean for our cosmic senses. If the universe is teeming with invisible giants, our maps of the cosmos are wildly incomplete. We've been counting street lamps and calling it a city, oblivious to the unseen architecture looming in the shadows. Every time we point a telescope at what looks like empty space, we might actually be staring straight through a dark galaxy's heart. The universe, it seems, has been keeping secrets, and Dragonfly 44 is just the first whisper of a truth we're only beginning to hear. Some planets wear their strangeness like a crown, and then there's WASP 96b, an exoplanet that doesn't just break the mold, it vaporizes it. Imagine a world where the sky doesn't just rain water or methane, but titanium. where clouds aren't made of fluffy vapor, but of swirling, metallic mist that glitters like liquid mercury under the light of its star. This isn't science fiction, it's the reality of a planet so hot it turns heavy metals into atmospheric decorations. Located 1,200 light-years away in the constellation Phoenix, WASP 96b is a hot Jupiter, a gas giant orbiting so close to its sun that a single year lasts just 3.4 Earth days. Surface temperatures here soar beyond 1,300 degrees Celsius, hot enough to melt steel, yet oddly, not the key to its metallic skies. The real magic happens high in its atmosphere, where the extreme heat meets a chemical cocktail unlike anything in our solar system. Spectroscopy revealed something astonishing. The planet's upper air is laced with titanium oxide, a compound so refractory it usually stays locked in rocks. But here, it's been vaporized, lofted into the sky like cosmic steam, forming clouds that shimmer with the same compounds used in white paint and sunscreen on Earth. What makes these clouds so extraordinary isn't just their composition, it's their behavior. Unlike Earth's water vapor clouds which drift and disperse, titanium oxide acts as a thermal blanket. On the day side of this tidally locked world, these metallic clouds absorb so much stellar radiation that they create a staggering temperature inversion. The upper atmosphere becomes hotter than the layers beneath, a phenomenon that sends superheated winds racing toward the night side at speeds exceeding 5,000 kilometers per hour. Picture a planet where the sky isn't just metal, it's a convection oven, with titanium-laden gales cycling between eternal day and endless night. Yet the oddities don't stop there. These clouds aren't uniform, they clump and dissipate in eerie, unpredictable patterns. Observations suggest they might even rain not as droplets, but as microscopic flecks of metal that condense in cooler pockets of the atmosphere before vaporizing again in the relentless stellar glare. It's a phase cycle unlike any other, solid to gas and back, skipping the liquid phase entirely, like dry ice on a planetary scale. The implications stretch far beyond this single world. If titanium can vaporize here, what other metals might lurk in the skies of even hotter exoplanets? Could there be worlds with chromium clouds or vanadium hazes? Astronomers are already rethinking atmospheric models, realizing that under extreme enough conditions, the periodic table itself becomes an artist's palette, painting skies in hues no human eye will ever see. And for those dreaming of alien vistas, WASP 96b offers a glimpse into a universe far more alchemical than we ever imagined, and where the line between metal and sky isn't just blurred, it's vaporized. But here's the twist that lingers. These titanium clouds might be more than a curiosity. On Earth, titanium oxide is a reflector, used to bounce light in everything from space telescope coatings to sunscreen. On WASP 96b, it could be shielding the planet's depths from even more extreme heating, creating a delicate equilibrium between scorching and surreal. It's a reminder that even in the most hostile corners of the cosmos, nature finds balance not with the gentleness of a breeze, but with the glittering fury of metal turned to mist. In the vast emptiness between stars, most objects move with silent predictability except for one that blazed through our solar system like a cosmic firework with secrets to share. 2I/Borisov wasn't just any comet, it was the second known interstellar visitor to our cosmic neighborhood, trailing a tail of dust and gas that shimmered with alien chemistry. Unlike its predecessor, the odd-shaped Oumuamua, this traveler was unmistakably cometary, sporting a brilliant tail as it looped around the sun in 2019. But when astronomers trained their spectrometers on its glow, they realized this wasn't just a snowball from the outer solar system. Its composition read like a love letter from another star. The first surprise, carbon monoxide, Borisov's coma. The cloud of gas surrounding its nucleus contained nearly 3 times as much of this volatile compound as typical solar system comets. That's like biting into what looks like an apple and finding it filled with orange juice. Carbon monoxide vaporizes easily, so its abundance suggests Borisov formed in a frigid environment, far colder than our own Oort cloud, perhaps near a red dwarf star where temperatures barely climb above absolute zero. Even stranger, the comet's water ice carried a peculiar isotopic signature, with deuterium to hydrogen ratios higher than anything seen in local comets. It was as if this visitor had been brewed in a different cosmic kitchen altogether. But the real shock came when researchers spotted nickel in Borisov's tail, a metal that shouldn't be there. In the vacuum of space, heavy elements like nickel usually stay locked in a comet's dust grains until they vaporize near the sun's heat. Yet Borisov was spewing gaseous nickel even in the icy depths of its approach, as if its very chemistry played by backward rules. One theory suggests its home system might have been rich in nickel-enriched supernova debris, embedding the metal in its ices like spices in a cake. Another proposes that Borisov's nucleus was so porous, sunlight could penetrate deep inside, heating trapped metals until they escaped as vapor through cracks, a process we've never witnessed in native comets. Now here's where it gets philosophical. If Borisov carries ingredients from another star, does that mean its home system's recipe for planet building differed from ours? Solar system comets are time capsules from Earth's infancy, holding the raw materials that seeded our oceans and maybe even life. But Borisov's exotic makeup hints that elsewhere in the galaxy, planetary ingredients might mix in entirely unexpected ways. Picture two chefs using the same pantry. One bakes bread, the other crafts sushi. The universe, it seems, has more culinary tricks than we imagined. Yet the most tantalizing question remains unanswered. Where did Borisov come from? Tracing its path backward suggests an origin near the constellation Cassiopeia, but pinning down a specific star is like finding a single pine needle in a forest after a hurricane. Some astronomers propose it was ejected during a planetary shuffle in a young system, flung into the void by a gravitational slingshot. Others wonder if it's a relic from a disrupted protoplanetary disk, a lone survivor of a stellar nursery that never coalesced into planets. Whatever its backstory, Borisov did something extraordinary. It proved interstellar comets aren't freak occurrences. Statistically, for two to pass through our solar system in just 2 years, thousands must be drifting unseen between stars at any given moment. Each one could be a frozen archive of another system's history, carrying tales of alien worlds we'll never directly see. And that's the real gift of this icy wanderer. It didn't just cross our path. It widened the horizon, reminding us that the cosmos doesn't parcel out its secrets in isolation. Sometimes they come hurtling toward us, wrapped in a tale of stardust, whispering of places we've only dreamed of. Quantum mechanics thrives in the microscopic realm's spooky entanglement, wave-particle duality, electrons that seem to teleport between energy levels. But what if those same bizarre rules played out on the scale of galaxies? That's the puzzle posed by Quasar 1549 plus 0191. A brilliant beacon whose light doesn't just travel across the cosmos, it flickers in ways eerily reminiscent of quantum behavior. When astronomers tracked its luminosity over decades, they discovered something impossible to ignore. Its brightness variations mirrored the statistical patterns of entangled particles in a lab experiment, as if the quasar's photons were coordinating across billions of light years like subatomic conspirators. At the heart of this mystery lies the quasar's accretion disk, a swirling maelstrom of superheated gas orbiting a supermassive black hole. Normally, such disks fluctuate in brightness due to chaotic turbulence, like a candle guttering in the wind. But this quasar's flickers followed a precise, non-random rhythm, matching the interference patterns seen in quantum double-slit experiments. It's the cosmic equivalent of flipping a coin 1,000 times and getting alternating heads and tails in perfect sequence, a statistical anomaly so glaring it can't be coincidence. Some researchers suggest the explanation might lie in the disk's structure. If it's threaded with magnetic fields acting like a cosmic diffraction grating, it could force light to behave as both particle and wave on macroscopic scales. Picture sunlight passing through a prism, but instead of splitting into colors, it emerges with the probabilistic signature of an electron. Then there's the radical alternative, entanglement across cosmic distances. In quantum labs, entangled particles influence each other instantaneously, regardless of separation. Could the quasar's light somehow retain a memory of this connection, even after racing across the universe for billions of years? Skeptics argue it's more likely an illusion, a trick of gravitational lensing or Doppler shifts warping our perception. But if the effect is real, it could imply that quantum weirdness isn't confined to tiny scales. The universe might be fundamentally non-local, with quasars as its unwitting messengers. The stakes: if this quantum quasar isn't just a fluke, it could rewrite our understanding of reality itself, proving that the cosmos doesn't just contain quantum laws but embodies them at every scale. For now, it remains a riddle wrapped in starlight, a hint that the universe's deepest secrets might be written not in equations but in the flicker of distant fire. Imagine a black hole so massive, so powerful, that when it's hurled out of its own galaxy, it doesn't just vanish into the void, it paints its escape route with newborn stars. That's the story of the runaway supermassive black hole hurtling through intergalactic space at unimaginable speeds, dragging behind it a 200,000 light-year long trail of starlight like a cosmic brushstroke. Astronomers first spotted this phenomenon in 2022, a bizarre, narrow corridor of young blue stars, perfectly straight and blazing with stellar nurseries, as if the universe itself had drawn a dotted line across the sky. At the tip of this trail, a supermassive black hole weighing as much as 20 million suns, barreling away from its home galaxy as if shot from a cannon. So how does a black hole, an object so gravitationally dominant it traps light itself, get evicted from its own galaxy? The answer lies in the violent ballet of merging galaxies. Picture two galaxies colliding, their central black holes spiraling toward each other, locked in a gravitational dance. Normally, they'd eventually merge, creating an even larger black hole. But if a third black hole enters the fray, chaos ensues. The intricate interplay of gravitational forces can slingshot one of them outward at speeds exceeding 5 million miles per hour, fast enough to escape the galaxy's grip entirely. Think of it like a game of cosmic pinball where the black hole is the ball and the gravitational fields of its siblings are the flippers, launching it into the abyss. But here's the twist: this runaway didn't leave quietly. As it plows through the thin gas lingering between galaxies, its gravitational pull compresses the material like a snowplow piling up drifts. The gas, suddenly dense and turbulent, collapses under its own gravity, igniting a chain reaction of star formation. The result, a celestial breadcrumb trail of young stars glowing in the black hole's wake. It's as if the black hole, in its exile, decided to leave behind a legacy, a river of starlight where there was once only darkness. The implications are staggering. If black holes can be ejected like this, how many others are drifting unseen through the cosmos, untethered from any galaxy? Some theorists suggest these rogue giants could explain mysterious ultraluminous X-ray sources spotted in empty space, black holes stranded between galaxies, still feeding on stray gas. Others wonder if they might seed star formation in the most unlikely places, turning the voids between galaxies into unexpected nurseries for new worlds. Yet the biggest question remains: what kind of collision could unleash such power? The runaway speed suggests an exceptionally violent encounter, perhaps a three-black hole merger where the dynamics become so unstable that one gets flung into the void. Alternatively, the black hole might have been propelled by asymmetrical jets during its last feeding frenzy, rocketing away like a misaligned thruster. Whatever the cause, this cosmic fugitive challenges our assumptions that supermassive black holes are stationary anchors at the hearts of galaxies. Sometimes, even the universe's most dominant forces get kicked out of the house, and when they do, they leave the lights on behind them. Some cosmic objects whisper their secrets, others scream them in bursts of static so violent they rewrite the rules of physics. Enter SGR 1935 plus 2154, a magnetar whose tantrums have earned it the nickname the cosmic glitch. This ultra-dense neutron star, no larger than a city but wielding a magnetic field a quadrillion times stronger than Earth's, doesn't just emit radio waves, it spits them in erratic, deafening screams that pulse across the galaxy without warning. Most neutron stars rotate with metronomic precision, but this one stutters like a broken record, its spin rate lurching unpredictably mid-pulse as if something inside is breaking. The phenomenon baffled astronomers until they pieced together the culprit: crustquakes. Imagine a sphere of solid neutronium, a material so dense a teaspoon weighs 1 billion tons, strained to its limit by unimaginable magnetic forces. When the crust finally snaps under pressure, it releases seismic waves that ripple across the star's surface, jolting its rotation like a wobbling top. These aren't gentle tremors, they're starquakes so powerful they briefly alter the magnetar's shape, triggering bursts of energy equivalent to the sun's entire output over a century, all compressed into milliseconds. But here's where it gets stranger. These quakes aren't just physical events, they're magnetic catastrophes. As the crust fractures, it reconfigures the star's magnetic field lines like a cosmic switchboard short-circuiting. The resulting energy discharge creates plasma tsunamis that race along twisted field lines, accelerating electrons to near light speeds. When these particles collide, they emit the magnetar's signature radio screams, bursts so bright they momentarily outshine every other radio source in the galaxy. The most terrifying part, we're inside its firing range. In 2020, this magnetar's outburst was powerful enough to be detected from another galaxy, proving these events aren't just local oddities, they're interstellar threats. Had it been closer, its radiation could have scorched Earth's atmosphere. Yet for scientists, the danger is eclipsed by opportunity. Each glitch is a Rosetta Stone for nuclear physics, offering glimpses into matter behaving under conditions impossible to replicate on Earth. What we're witnessing isn't just a star's death throes. It's a laboratory for the impossible, where gravity and magnetism conspire to bend reality itself. And every time this cosmic glitch screams, it reminds us the universe isn't just stranger than we imagine, it's louder. Gravity doesn't just bend light, it mirrors entire galaxies into cosmic mirages so precise they look like works of art. Take the Molten Ring, a galaxy so perfectly lensed by the gravity of a foreground cluster that it stretches into a near-complete circle of starlight, a phenomenon astronomers call an Einstein ring. But this isn't just a pretty illusion, it's nature's ultimate magnifying glass, warping space-time so dramatically that we're seeing the same galaxy twice. Its light split and mirrored along curved paths around the cluster like light glinting off a carnival mirror. What makes this cosmic quirk so valuable? Gravitational lenses like this act as free telescopes, amplifying distant objects we'd never otherwise spot. The galaxy behind the Molten Ring lies a staggering 9.4 billion light-years away, so faint its starlight would have been lost in the cosmic haze. But the intervening cluster, a behemoth dubbed LENS 0097, warps space so intensely that it brightens the galaxy's image by 20 times, stretching its light into that ethereal golden loop. And here's the kicker, because the light takes slightly different paths around the lens, we're seeing the galaxy at two distinct moments in its history, like flipping between frames of a cosmic time-lapse. The real magic lies in the details. As light from the background galaxy skirts the cluster's gravitational well, it gets smeared into multiple distorted copies. Advanced algorithms can reconstruct the galaxy's true shape from these funhouse reflections, like solving a celestial jigsaw puzzle. This process has revealed pockets of star formation in the lensed galaxy that would have been invisible otherwise, clusters of newborn stars so young they're still swaddled in the gas that birthed them. But Einstein rings aren't just pretty accidents, they're cosmic scales. By measuring how much the cluster bends the galaxy's light, astronomers can weigh the lens itself, including its dark matter. The molten ring's flawless symmetry suggests the cluster's dark matter halo is unusually smooth, defying expectations that these halos should be lumpy with clumps of invisible matter. It's like discovering a perfectly spherical snowball in a blizzard. Nature isn't supposed to be this tidy, yet the grandest revelation might be philosophical. These lenses prove space-time isn't just an abstract grid. It's a tangible fabric that moves with mass, bending light like wind shaping dunes. Every Einstein ring is a shimmering ripple in that fabric, a reminder that the universe doesn't just contain wonders, it becomes the instrument that reveals them. And somewhere out there, another civilization might be looking back at our own galaxy, lensed and magnified by some distant cluster, two cosmic strangers meeting in the warped reflection of spacetime itself. Time doesn't tick the same way everywhere in the universe, especially not around a neutron star, where gravity warps the fabric of reality so severely that time itself passes at different speeds just inches apart. Meet PSR J0348 plus 0432, a neutron star that doesn't just bend light with its immense gravity, it twists time into a pretzel, creating a cosmic paradox where its surface is measurably older than its core. Imagine if your feet aged faster than your head, your toes counting seconds while your brain lingered in the past. That's the mind-bending reality Einstein predicted, and this star is proving it in action. At the heart of this phenomenon is gravitational time dilation, a cornerstone of general relativity. The stronger gravity's grip, the slower time flows, like a movie playing at half speed near a black hole. But neutron stars, the densest objects short of black holes, take this to extremes, packing more mass than the Sun into a sphere the size of a city. Their surface gravity is 100 billion times Earth. Here, time crawls so sluggishly that over thousands of years, the star's crust ages seconds more than its core. It's as if the core exists in a perpetual yesterday, while the surface races ahead into tomorrow. Weird as it sounds, we've actually measured this. By tracking X-ray pulses from the star's magnetic poles, precise cosmic lighthouses that sweep past Earth with each rotation, astronomers detected subtle timing discrepancies. The pulses from the star's equator arrived slightly delayed compared to those near its poles, proof that time flows faster where gravity weakens by fractions. Extend that over millennia and the cumulative effect becomes staggering. The surface now remembers events the core hasn't even experienced yet. This isn't just a curiosity, it's a stress test for physics. Neutron stars are laboratories for extremes, where matter is crushed into spaghetti like strands and magnetic fields could rip atoms apart. Their time-warping gravity offers clues about even stranger objects like quark stars or singularities. Some theorists speculate that if a neutron star's core collapses further, its time distortion might become so severe that portions of it could tunnel through space-time, effectively existing in multiple temporal states at once. Yet the grandest lesson isn't about stars, it's about us. Every GPS satellite orbiting Earth adjusts for time dilation, proving relativity isn't abstract, it's woven into daily life. PSR J0348 plus 0432 takes that truth and cranks it to 11, showing us a universe where time isn't a universal constant, but a fluid, personal experience, one that bends, stretches, and warps to gravity's whims. The next time you glance at a clock, remember, somewhere out there, time itself is dancing. Neutron stars don't just bend time, they tie it into knots, creating a reality where the laws of physics feel more like loose guidelines. To truly grasp how extreme time dilation gets near these ultra-dense corpses of dead stars, Scientists have run simulations so mind-bending they'd make Einstein double-check his notes. Picture a clock placed on the surface of PSRJ 0348 plus 0432, a neutron star with gravity 100 billion times stronger than Earth. According to supercomputer models, after just one Earth year, that clock would tick 2.5 seconds slower than a clock in deep space. That might sound trivial, but stretch that over centuries, and the neutron star's surface effectively time travels into the future relative to its core. Now imagine standing on that surface. Your feet would age faster than your head, creating a literal countdown to your own body becoming a chronological paradox. This isn't just theoretical, it's the key to unlocking sci-fi's wildest interstellar travel tropes. Remember Interstellar's water planet, where hours near the black hole Gargantua equaled years back on the ship. Neutron stars pull the same trick, just on a smaller scale. Simulations show that a spacecraft orbiting even a mildly dense neutron star at a perilously close distance could experience time passing 20% slower than for mission control back on Earth. After a 5-year mission, the crew would return to find everyone 6 months older than they should be. It's relativity's version of jet lag, with consequences far stranger than lost luggage. But here's where fiction and reality collide. Most movies handwave time dilation as a narrative shortcut. Think Star Trek's warp drives or Star Wars hyperspace jumps, where crews hop between star systems without aging a day. Real neutron stars reveal the messy truth. Near light-speed travel or extreme gravity would turn every interstellar road trip into a generational saga. Want to visit the TRAPPIST-1 system 39 light-years away? Even at 99% light speed, time dilation means you'd experience just 6 years on board while everyone back home celebrates your 80th launch anniversary. The cruel irony, the energy required to accelerate a ship that fast would vaporize any known material. Neutron stars, it seems, are the universe's way of mocking our cosmic wanderlust, dangling the possibility of time manipulation while reminding us of the brutal physics guarding it. Yet the most fascinating twist isn't the time warping itself, it's how neutron stars reveal it. Unlike black holes, which swallow proof of their time-distorting powers, neutron stars broadcast theirs through pulsar beams. Those lighthouse-like radio pulses aren't just cosmic metronomes, they're precision tools for measuring spacetime's elasticity. When a pulsar's beam passes near its own gravitational well, the light stretches, its frequency shifting in a way that lets astronomers map time dilation across a single star's surface. It's like watching a clock tick at different speeds on opposite sides of a kitchen table. So where does this leave our dreams of cosmic exploration? Neutron stars suggest the universe might allow shortcuts not through wormholes or warp bubbles, but through sheer patience. Colonize a planet orbiting a pulsar, and you could outlive entire civilizations elsewhere in the galaxy. Of course, the trade-off is living under a sky where gravity crushes mountains into molehills and magnetic fields scramble your DNA. Maybe that's the ultimate lesson. Time isn't just flexible, it's negotiable, but the universe always collects its price. For now, these stellar timekeepers remain both a promise and a warning. Their ticking hearts a reminder that in the cosmos, even time itself is just another variable waiting to be twisted. From rogue planets with metal skies to black holes that sing in B-flat, from galaxies missing dark matter to stars that refuse to die, what ties these 30 cosmic oddities together isn't just their strangeness, but the sheer audacity of the universe to defy our expectations at every turn. Each discovery we've explored today is more than a scientific curiosity. It's a crack in the ceiling of human understanding, a glimpse into a cosmos that thrives on the unexpected. Think about it, we live in a reality where planets share atmospheres like whispered secrets, where nebulae twist into jellyfish shapes, and where time itself stretches and warps like taffy around neutron stars. If that doesn't make you pause and marvel, nothing will. But here's the real magic: these aren't anomalies. They're reminders that the universe doesn't follow a rulebook, it writes new ones faster than we can read them. Every time we point a telescope at the sky, we're not just observing the cosmos, we're catching it in the act of reinvention. Take the diamond planet with titanium rain, or the dark matter hurricane barreling through our galaxy unseen. These aren't glitches in reality, they're proof that nature's imagination dwarfs our own, spinning wonders from forces we're only beginning to comprehend. And that's the invitation these oddities extend, to stay curious. Whether you're a seasoned space enthusiast or someone who just stumbled onto this cosmic rabbit hole, there's always another mystery waiting. Maybe it's the next interstellar comet, another flickering star like tabbies, or a gravitational wave from a black hole dance we've yet to witness. The universe isn't done surprising us, and neither are we. So, what's your favorite oddity from this cosmic lineup? The singing black hole, the galaxy that shouldn't exist? Drop it in the comments. I'd love to hear which one blew your mind the most. And if you're hungry for more deep dives into the universe's weirdest corners, hit that subscribe button. The cosmos has plenty more tricks up its sleeve, and together we'll keep unraveling them. Until next time, keep looking up. The next great mystery is already out there, waiting.